Welcome to our week 8 video. This one's titled Developing Exponential and Logarithmic Functions. So we're going to look at developing log functions, exponential and logarithmic functions, and we're going to use simplified models. If you remember, when we looked at graphing exponential functions, we had 4 constants, a, b, c, and d. We're coming up with simplified models to develop our functions. These just have 3 constants, a, b, and c. So for the exponential functions, this is the model we're going to be using, and for logarithmic functions, this is the model we're going to use. So we're going to start by looking at developing models using graphs. So we're going to look at a graph, and then we're going to use our knowledge of exponential and logarithmic functions to create a model for that function. So fx equals such and such for exponentials and logs. And I do that based on the values of a, b, and c. So if we look at an example, determine a possible exponential rule for the graph shown here. From the graph we can see we've got a horizontal asymptote. So aside from telling us it's exponential, we know it's an exponential equation because we have a horizontal asymptote at y equals 3. We've got a y-intercept at 2 and x-intercept at -2. And we're going to use these 3 values to come up with values for a, b, and c, and then as a result come up with our model for this graph. So as you can see, we've got an asymptote here at y equals 3. That is our c value. Okay, so if you remember when we looked at graphing them, exponential functions, the c, or the constant, was the asymptote. So we can straight away from our graph say that the c value is 3, and so we can come up with our model that fx equals a e to the power of bx plus 3. So that's the first constant discovered. The second one we're going to look at is we're going to use this y-intercept. So we know that y equals 2. So the value of x, when x equals 0, y equals 2. So all we do is substitute those 2 values, 2 and 0, into our equation. So when y equals 2, that equals a e to the power of b times 0 plus 3. Now e to the power of 0 is 1. So this next line here, all I've done is subtract 3 from both sides. So we have 2 minus 3 equals a times 1. So a equals -1. So we can update our model now. That is fx equals -1 e to the power of bx plus 3. And we're going to finally use this final value, our x-intercept of -2, to calculate b. So again, what we do, we plug in into our equation or into our model, the model we're working with. When x equals 0, when y equals 0, y equals 0, -1 e to the power of -2b plus 3. So here, the -2, that's our x value, that point there. So again, we just substitute these values in, subtract 3 from both sides, so we get -3 equals -1 e to the power of -2b. When it's in this form here, we take the natural log of both sides, so when we take the natural log of 3, and we take the natural log of e to the power of -2b, that simplifies down just to log 3 equals -2b, and from there we can work out that b equals log 3 divided by -2. So now we've got our a, b, and c values. We can say that our model for this graph is given by -e 0.55x plus 3. Okay, so that's how we can develop an exponential equation based on a graph. We're going to do something similar now for the logarithmic functions. So determine a possible logarithmic rule for this graph shown here. So we've got our vertical asymptote at x equals -1, a y-intercept at 1, and an x-intercept at e to the power of -1 minus 1. So again, we're going to use those three values to come up with our rule. So when we have a logarithmic function, log 0 is undefined. So this asymptote here is where it becomes undefined. So it's going to become undefined when x plus 1 equals 0. X plus b equals 0. So if you remember, our general rule was a log x plus b plus c. We want to work out that since at x equals -1, that becomes undefined. The only way that, so if x plus b equals 0 and x equals -1, then b must equal 1 in order to have log 0 be undefined, which is when our asymptote is. So our b value here is 1, just like I've got written here, so that should be a b, because that's our general rule. So our asymptote occurs when we have log x plus b equals log 0. So minus 1, which is where our asymptote is, plus b equals 0, therefore b equals 1. So this is our simplified function, a log x plus 1 plus c. The next point we're going to use is our y-intercept. So when x equals 0, y equals 1, so we just substitute those two values into our modified equation. So 1 equals a log 0 plus 1, which is just 1 plus c. Log 1 is 0, and so that gives us a times 0 plus c equals 1, therefore c equals 1 as well. So I should just try and get my pen working. That should read log times 0. So now we've got our updated function here, our c value of 1. We just need to work out this a value. And so again, we use this y, the x-intercept. So when y equals 0, x equals e to the power of -1 minus 1. So again, we just substitute those values in. So this gives me a log e to the power of -1. Again, this pen not working, doesn't matter. That minus 1 plus 1 should cancel out, so that bracket should be there. So we've got minus 1. So a equals -1 divided by log e minus 1 to give us a value of a equals 1. So again, just using the x-intercept and y-intercepts, substituting those values in, and we can work out those three variables a, b, and c, and come up with our model, a potential model for this equation. Now it's just based on those 2 points in the asymptote, so it's one potential model, and for this one we get 1 log x plus 1 plus 1. We can also look at creating models using logarithmic transformation. So what we're going to look at here, this is our exponential, an equation for an exponential. If we take the log of both sides, so we've got log y equals log a, our brackets a e to the power of kx, that simplifies down to log y equals log a plus log e to the power of kx, so that's just using our log rules, which then simplifies further to log y equals kx plus log a. Now this is in the form now of a equation of a straight line, where y equals mx plus c. So what we can do is that if we've got a exponential equation given like this, we can revert it to a straight line to make it easier for us to calculate these k and a values. So if we look at an example now, so we've got data here. So a microbiologist from a lab counts the number of viruses in a blood sample from an ill patient. The results are summarized below. The virus continues to grow in this way. After how many days will the number in the viruses in the patient's blood sample exceed 1 million? So these are our data points. So if we graph them, this graph here on the left is the exponential growth. That's the data, the actual data values. What we're going to look at doing now is, just like we had in this equation here, we took the log of the y values equals kx plus log a. What we do down here, our number of viruses is our y value, so we're going to take the log of the number of viruses. So we take the natural log of these number of viruses, so log 7, log 55, log 1073, and so on, and we plot that against the number of days. So number of days on the horizontal, on the vertical is the log of the number of viruses. And as you can see here, we get a nice straight line. And from that line, we can create an we can work out the equation of that line. And from that equation of that line, we can work out our a and k values based on this relationship here. So remember, when we're coming up with an equation, we can start by finding the gradient. And to determine the gradient, we just need 2 points. So using 2 points, so I'm using 3, 4. So 3 and log 4. So make sure you use that second value, and 8 and 9. So those two values I'm using to work out my gradient. y2 minus y1 equals x2 minus x1. And so I get a gradient of 1. Now, we know our equation of a straight line is y equals mx plus c. So I can use a third point, so in this case 11, 12, to find out that constant c value or the y-intercept. So I just substitute those values in along with the gradient I've just calculated. So here 12 equals 1 times 11 plus c, therefore c is going to equal 1. So the equation of that straight line is y equals mx, so y equals x plus 1. Now we're going to take that equation of a straight line and relate it back to this log equation. So log y equals kx plus l, natural log of a. Now k is the same as our gradient, so in this case our gradient was 1, so k equals 1. And log a is our c, our y-intercept, so in this case c, so log a equals 1. So if log a equals 1, that means a equals e to the power of 1, which is just e. So that's just using our, if it's written in that form, our log laws say that we can rewrite it as a equals e to the power of 1. Okay, so we've worked out our k and our a values. So back to our exponential equation. Again, we're using a simplified model here just to make it a little easier for our calculation. So y equals e to the power of kx. Substitute our a and our k values. E times e to the power of 1x, which we can rewrite as ex plus 1. So the number of viruses equals e to the power of 1 plus the number of days. So if we're looking for when it is 1 million, we substitute 1 million in, natural log of both sides, subtract the 1, and we get that it takes 12.81 days. So in the 13th day, it's going to exceed 1 million viruses.